Okay, Bismillahirrahmanirrahim. Any questions before we begin? No? None? The homework is due today at 5 p.m. Everyone knows that. Submission is through LMS. There's going to be a quiz on Thursday, inshallah, on the camera model part, which is the previous module. Any other question, comment? All right, so last time we started our discussion of how we can understand the 3D of the world given more than one image or an image but some assumptions on it. And I talked about various different forms of information that are available inside the image to help us reconstruct the lost information in the projection. The 3D information is the information which is lost in the projection process, right? So one of the fundamental methods which is very interesting to look at is that of stereo. And the stereo problem in this is this, that you are given more than one image, right? So you have two cameras here, camera 1 and camera 2, looking at some 3D world. The world is not planar in general, it's a 3D world, okay? Which means points span all the three dimensions, all the three independent axes of the world. Now, if this is the case, if you have two cameras and you have known camera viewpoints, you know where those cameras are, then it is possible to reconstruct the 3D of the world. Okay. Any ideas why? How will we be able to get the lost information? So what happens if you have only one camera and you try to invert the camera model? Yeah. How? That's the problem. But how will you compute the depth? Yeah. I mean, there's a fundamental loss of information that has happened. What is that? You had a three-dimensional world and you took a projection of it in two dimensions. So now you have two dimensions only. Okay, so how will you reconstruct? And I'm saying it's possible to reconstruct those points in three dimensions from two camera images. Yeah. Exactly. So we have seen that a point in an image will back project to a ray, because really when you are forward projecting, when you're taking the projection, all points along that ray actually map to the same point in the image. So when you take a point in the image, you don't know where along that ray that point came from. But if you have two images, and you know this point is the same as that point in the second image, then this point will project to a ray and that point will project to a ray, and where those two rays intersect, that's really where. So you basically get an additional constraint on that ray, on the distance along that ray from the second camera. Okay, there is a biological motivation also for stereo vision. So we humans have two eyes, or many animals, all mammals have two eyes, and so what essentially happens is that your left eye looks at the world from a slightly different angle than your right eye. Okay, so both images are somewhat different. So if here is an illustration, so this image, if you look at this image and this image, they are somewhat different, right, in the arrangement of the pins here, and the difference between them actually is a function of the depth of the points. In fact, if the optical axes of your cameras are aligned, right, if you have two cameras, then the fundamental relationship, as we'll see, is that if the point is closer, you have more difference in the position of that point in between the two cameras. If the point is further away, then there is less difference. Okay, so which means that if you can find the difference between how much this point has moved between the left image and the right image, you can actually reconstruct depth out of that. And this is what our brain does. So both these images are fed into the visual cortex, which is at the back of the brain, and there is a matching process going on there. And so we can match that, okay, this object is the same, this object in the left image is the same as this object in the right image, and what's the difference that they generate in their position, that's resolved by our brain into depth. Okay, now we do that without realizing it, right? In fact, it turns out that so people who have only one eye are unable to do this. Now you might ask, well, they still perceive depth. It's not that. So if I close my one eye, I can still perceive depth. Okay, but that's because I told you that in perceiving depth, there are a lot of different cues that are at play, like occlusion, like shading, like texture, like I mean, there are so many. I mean, the angle between lines. There's so much training that has happened in our brain, so we still momentarily perceive depth. But the stereo cue goes away if you have only one eye. Okay, and that means that sometimes it happens that. So I had a friend who had only one eye. The second one didn't work, and so sometimes he would bump into a door or into something which I wouldn't. Okay, in fact, it also turns out that even amongst people who have two eyes, a certain percentage of the population, their stereo algorithm in the brain is not working. So, and often they go through life without knowing that it's not working. Okay. And then there are certain, so stereo does not work very well for objects which are far away, because like that clock, right? The clock is far away from me in this room, and the distance between my two eyes when I'm looking at that clock, the distance between the eyes typically is about 7 centimeters for people, or somewhere around that. I mean, there's some variation in that number. We call this the baseline distance. Now, the further away your baseline distance is, the longer your baseline is, the more depth resolution you can get, right? Because you will be looking at objects from further away viewpoints. Okay, so because this distance is only 7 centimeters, there is only a certain distance in the world, a certain depth in the world that you can perceive in stereo. Beyond that, the two images look practically identical. Okay, and this distance is about an arm's length or a little bit longer than that. Beyond that, your stereo doesn't work. So if I can perceive depth of objects far away, that's because of some other cue than stereo. Okay, so stereo comes into play for humans. It comes into play in doing actions like catching a ball, for example, or hitting a shot in cricket, for example. So if you are making a pull shot, you need to time the distance of the ball. The ball is coming at you at a fast speed. You want to time it very well with your bat, right? If you are a little bit early or a little bit late compared to the distance of the ball, you will miss it. Okay, so for these types of computations, stereo is very important. The stereo cue is very important, and so people whose stereo is not working well cannot be good batsmen or good cricket players, and often they don't know. They just think like, I can't do this, and other people can do this, but it's often a kind of disability in the visual cortex. Okay, driving and parking a car, planning and building a three-dimensional object, threading needle and sewing. Because a needle is a thin object, it's think of it as very, very thin. So it doesn't display any texture. It doesn't display any size cues and so on. It's kind of like an infinitesimally thin object. So to be able to judge where it is, stereo becomes very important. So if you want to pass a thread through the eye of the needle, stereo is crucial in doing that. In fact, some people you might see like close one eye and try to thread the needle. It's not a good idea if their stereo cue is working. Okay, reaching out to shake someone's hand, pouring into a container, stepping off a curb. These are all actions where you are judging the distance of nearby objects. And in that, stereo is very important. Okay. So here's an illustration of stereo. Where is the fundamental cue? So we have two cameras here. This is, let's say, camera 1, and this is camera 2, and they are looking at this 3D scene where there is this object, and behind it there is the second object. Okay. Now from camera 1 this appears like this, and from camera 2 this appears like this. Notice that this box appears moved. It's now on top of the fin, whereas here it was a large distance from the fin. This is really the cue that this distance has reduced here. This is really the cue that helps you construct for depth. This tells you that the box is closer to the cameras than the dolphin. Okay. And we can have algorithms that do this matching and then compute depth. This is a depth map. It's shaded. The gray level here is a function of distance z from the camera. Okay, so you see that this object is brighter because it's closer, and then this tail fin is darker because it's further away from the observation point. Okay. This is a stereo reconstruction of a human face. This is actually taken from a textbook where I'm taking some material from for this particular set of slides. It's called Treco and Veri. So this is one of the authors of the textbook. They're showing only one image, but actually they took two images. In fact, sometimes people do this trick that because human face is symmetric, instead of taking two images, they take one image and they flip it and they say, well, that's the second image. And since human face is approximately symmetric, that works. But here I think they took two images, and then from that, so it says here one image from a stereo pair. So they actually took two images, and then from that they constructed this 3D, which is actually a pretty decent 3D map. It's actually pretty accurate. Okay. So we want to see how we do this. So the fundamental relationship here is that the perspective transform, which we have seen, the camera model really, the perspective transform relates a 3D world point to its corresponding image point in 2D, and the link between the 3D point and the 2D point is through the camera parameters, the camera matrix, which is a 3x4 matrix P. It's through those camera parameters that the 3D world point maps onto the 2D world point. So now if I want to inverse this, the inverse perspective transform, if something like that exists, will relate an image point to a world point, but that does not have a unique solution. As we have already seen, it gives you a ray in the world rather than a unique point. And the reason you can't invert it mathematically, it's a 3x4 matrix. The inverse doesn't exist uniquely. And then physically we understand that all points on that ray are mapping to the same world point. So this is an illustration of that idea. So the perspective transform is that this point xyz is mapping to this point xyf really on the image plane, and then if I want to take that xy, invert it back, then I'll just get a ray, and all points along the ray were mapping to the same point. Okay. So that's where the idea of stereo comes in. What if I had two cameras? Yes. No. Yeah. No. From a single camera, whether it's orthographic or whether it's it's a good question. Let me come to that question in a moment. If the camera does rotate as well as translate, then yes, we can. And we'll see a method for that. Orthographic cameras also generate disparity, right? But it depends on the nature of camera motion. So if an orthographic camera only translates, then no. But if it rotates also, then yes. Okay. But a perspective camera, if it only translates, you can do. We'll see this as we go through this. Okay. So what if we have two cameras? Well, in this case, this is the forward projection. You have a scene point it's a particular point. It's clearly defined x, y, z. It's a well-defined point in 3 space, right? So you have a point. You will in two cameras. In the first one, you join it to the optical center. This is where the image becomes, you join it to the second optical center, this is where the image becomes. Okay, now if you did not know the point, you just knew these 2 points, what you can do is, well, invert this, so you get a ray in the world, you invert this, you get a ray in the world, where those 2 rays intersect. I mean, given only image 1, given only this image, well, this point could have been anywhere along this ray, right? Given only this image, this point could have been anywhere along this ray, but given both of them, you will realize that this is the only possible solution. Okay, and that's the fundamental idea of stereo. Okay, so the basic principle in this stereo computation is triangulation. I have 2 observations from 2 points, and from that I'm triangulating. This idea is also used in many other circumstances. For example, in computing your location from GPS signals, or indoor localization, let's say from Wi-Fi or Bluetooth signals, we still use triangulation. So that's the same idea. It's just that the sensor is now a camera. Okay, and 3D coordinates are computed from intersection of 2 rays. Now, to be able to do this mathematically, to be able to do this, I'm saying you require camera calibration and you require point correspondence. Why do you require camera calibration? Sorry? I don't know the world coordinates to begin with. I just have images, right? I'll take a picture here and a picture here, and from that I want to reconstruct this 3D world. I'm saying to be able to do that, I will require camera calibration. Why? Not really. I mean, you have a point there, but there is a more fundamental reason for that. We need the camera center. Yes, that's true, but something a bit more than that also. No, there's really no condition that focal length should be similar. We can do stereo with dissimilar cameras. Well, how do I back project a point? We have done that in the previous lecture, previous lecture, right? How do I back project a point? To be able to back project a point in an image, to be able to back project a point in an image, you either have this relationship, x lambda is equal to, what was it, p plus x, which is your input point, plus lambda c. Okay, so what is p plus? It's a function of p. And what is p? It's camera parameter. I mean, how would you compute the ray? You have to compute the rays to be able to intersect them. And that ray, this is that ray, x lambda. That ray depends on the camera parameters. This p is all camera parameters, and this c is also camera parameters. Okay? Or even if you were in the canonical view, well, both cameras can't be in the canonical view. If one of them is in the canonical view, the other one is not. Okay, but even if you were in the canonical view, you have a k inverse x type of relationship for d, right? So d is that direction of the ray, and so this k inverse is all the intrinsic parameters. So in the canonical view, because there are no extrinsic parameters, the extrinsic parameters are all identity. In the canonical view, you only need intrinsic camera parameters, but in the general view, and at least one of the cameras will be in the general view in the stereo problem, because they are both not at the same location. So if I fix the axis to one of them, the second one is in a general location, right? So in the general view, all the camera parameters are needed to construct the ray, not just the intrinsic parameters. Okay, so that's why I'm saying the camera has to be calibrated. Otherwise, how will I compute these rays? These rays are a function of camera parameters. Agreed? Is that point clear? Right? The back projection process will not happen if you don't know the camera parameters. All right. And the second thing that you need is point correspondences. You need to know that this point is the same as that point in the image. Why do you need that? Well, because the ray that I'm intersecting has to emanate from the same point. Right? So these are 2 fundamental things that you need to be able to do stereo. You need to have a method for point correspondence, and you need to calibrate your cameras, and then you will be able to do stereo. Okay, is that clear? Okay, so in that sense, stereo requires solving 2 problems. You have to solve the correspondence problem, which part of the left image and the right image are projections of the same seeing element. And then after you have done correspondence, you have the reconstruction problem. Given a number of correspondences from left to right image, and camera calibration information, what can we say about the 3D location and structure of the observed? So that's the triangulation process. I need to do that. Okay. We will see that there is a certain form of stereo that is possible even without camera calibration. But then the structure is not reconstructed properly. There's some distortion in the structure. Okay. So I'm just stating that for the purpose of completeness. If we do want to reconstruct the 3D structure as it looks in the world to us in a Euclidean frame, I mean the dimensions being correct and so on, then camera calibration is essential. There is a projective distortion, a 3D projective distortion of that structure that can be computed without camera calibration, but that's not of interest right now to us. All right. Okay, so one of the fundamental things when we talk, so I've given you the idea of stereo. Now let's start to dig into it a bit. So one of the fundamental things that we find in stereo when we are trying to find corresponding points between image 1 and image 2 is what we call the epipolar constraint. Okay, and the thing is, what will happen is that you will find an object in image 1, let's say a point in image 1, and you would need to know where that point is in image 2 to be able to do correspondences, right? We have not so far looked at automatic methods to do correspondences. Okay, so far what we have done is, okay, even when we were computing the homography, let's say somebody gives us the correspondences, then we know how to estimate the homography. Okay, for now we can assume that, but in a real system, what will happen is that there will be no user marking correspondences for you. You will have to have an automatic method to find correspondences, which is our next module. We will talk about those methods in considerable detail. Okay. Now, in such a method, what happens is that you pick an appropriate point in one of the images and you go all over the second image and you search where a matching point is. So it's kind of like a matching process that you do. Okay. Now, given one of the interesting things that happens in the stereo problem is that you do not need to search for the matching point all over the image. Okay, which is the epipolar constraint. We say if you pick a point in, let's say, the left image, in the right image there exists a particular line along which the match must be. It can't be anywhere else in the image. Okay, and that's called the epipolar constraint. It's a fundamental constraint in stereo. It improves the accuracy of your stereo method for point correspondences. It helps you search for point correspondences more efficiently. Okay, and it's a pure geometric constraint. It's a constraint derived from camera geometry, and let's look at that. Why does such a constraint exist? So the epipolar constraint states that the corresponding point in the second image must lie along a special line, which is called the epipolar line. Okay, I'm just stating the constraint for you. Now let's see why that constraint exists. We can see that purely by geometric reconstruction, construction. Okay, so I have a world point P. This is, by the way, an unknown point right now. That's what I'm trying to reconstruct. Okay, but I have a world point P and I have a camera O1. Okay, which has axes x1, y1, z1. That's the camera coordinate frame for this camera. And so the image of that point will be formed by joining P to O1 and finding the intersection with the image plane, which is this boldface P here. Okay. Now, what will happen in the second camera? In the second camera, if I take this point, let's say the point was known, where will it be imaged? It will be imaged here in P prime. Okay, this is some other camera coordinate frame x2, y2, z2. Okay, so it will be imaged here. But actually, I don't know where P is, where this cap P is, right? This is an unknown. So let's say I'm trying to search for that. I'm trying to search for those correspondences here. So let's say P was not here. P was actually here. Okay. In that case, what will happen? The corresponding image should have been here. And let's say P was here. Then the corresponding image should have been here, and let's say P was here, then the corresponding image should have been here. Okay. Now, what is known is the ray. As soon as I know this image point and the camera calibration parameters, I know this ray, right? This ray is known. So it can't be anywhere else. And if this ray is known, then this line can be known in the other camera coordinate system. Okay. In fact, I can keep moving this point all the way to the camera center here and all the way to the other side to infinity, because those are all the possible positions of that world point P, and I'll get a line that emanates from this point and it goes across the image. Okay. Why is it a line, by the way? Why is it not a curve? Can somebody prove that it's a line? It's parallel to this line? No, not necessarily. This line is parallel to that? No, not really. No, this camera could be rotated with respect to that ray, and so then the image frame is not parallel to that line. If the image frame is not parallel, this line exists in the image frame. So there is no condition that the image frame here should be parallel to this line. I'm asking for a proof, a simple proof that this is indeed a line. The epipolar line will always be a line and not a curve. But yes, because the projection process preserves straight lines. We have already seen this as line in 3D. I proved this quite meticulously, both geometrically and algebraically, that a straight line in 3D maps to a straight line in 2D. Okay, and so because this ray is a straight line, and so that straight line, this line is nothing but the projection of that ray. Okay, and so this completes my proof. This tells me that when I'm searching for a corresponding point, I have a point in one image, I'm searching for a corresponding point in the second image. It can't be anywhere, it must be along a particular line, which is actually the projection of that ray. All right? Agreed? Okay, so this line is called the epipolar line. That's the name for this. And this point in particular is called the epipole. What is the epipole? The epipole is the image of the first camera center in the second camera. Okay, that's the epipole. Why is the epipole significant? What's some special property of the epipole? Yeah.
All epipolar lines will originate from this.
Exactly. Very good. All epipolar lines will pass through the epipole. Okay, because consider some other point. What will happen? How will I project a ray for that? I will join this to that point, and that's the ray. Okay, and that ray will project to find some other epipolar line here, but all rays for any image point must be joined to the camera center. That's the fundamental property of the pinhole camera. They must be joined to the camera center, and therefore all epipolar lines will pass through the epipole. So an epipole is a very significant point in computing epipolar lines or working with epipolar lines, because an epipolar line has to pass, every epipolar line has to pass through the epipole. Yeah. The epipole is the image of the second camera center. Okay. Now how do you image any point in the world? You join it to the camera center. Okay, and find the intersection with the image plane. So that's why the epipole is significant, because the epipolar lines are nothing but projection of those rays. Okay, so those rays will all pass through the camera center, which means all epipolar lines will pass through the epipole. Okay, so what is the epipole? The epipole is the image of the second camera center. If you took two pictures and the other camera, one camera was visible in the other camera, then that's where the epipole would be. The epipole is just not in the image plane, but it still exists. Right? If for example there are two cameras which are perfectly just different by a translation in one axis, right? Yani their imaging planes are perfectly parallel, then the epipole is at infinity, because that's where the epipolar lines will match. Right? Okay, so here's an example. This is I'm showing you a stereo pair, two pictures of a scene. So this is a picture and this is another picture. Let me flip through them just so that you see. These are taken by two different viewpoints which differ both in rotation and translation. It's not just a pure rotation. If it was a case of pure rotation, then the image would be perfectly related by a homography anyways. We know that. But now the image is not perfectly related by a homography, something that you proved in problem 4 of your homework, if you are done with problem 4. Okay. So now what do the epipolar lines look like? So this is, by the way, epipolar lines exist in pairs. There's an epipolar line given a point in one image, there's a line in the second image. If given a point in that image, there's a line in this image. So epipolar lines are in pairs. Everything along that pairs of epipolar lines actually relates to the same 3D world points. Okay. Now these are the set of epipolar lines. I won't tell you how I computed them for now. We will do that later. Okay. But notice, for example, notice, well, one thing, the epipole is not in the frame. I don't see it, but you can imagine where it is because the lines are converging. So they are converging towards the epipole. The left image has an epipole in it and the right image has an epipole in it. Now notice that, for example, this point of the window is along here, the same line passes through it. Okay, this point here, the same line passes through it. But this is at a different depth. It was sort of a plane, so you might think that's a homography, but even things which are at a different depth. Okay, so for example, in this image, this line is passing just above this edge, and this image, this line is passing just above this edge, and that's a different plane than this plane. So it can't be a homography relating them. Okay, and similarly, it passes here just at where this break is, and it passes here just at where that break is. Okay, and cuts this pipe somewhere in the middle and cuts this pipe somewhere in the middle, and so on. It holds for all those lines. There's a line passing through the tip here, and there is a line passing close. Well, we don't see the tip here, so I can't really convince you of that. There's a line passing, let's say, the bottom of this drain pipe, and it's here at the bottom of this drain pipe. Okay, now so there is kind of a correspondence between these images. Okay, but don't confuse this with a homography, because a homography is a point-to-point correspondence. A homography is a correspondence where I know this point maps to this point. This is not a point-to-point correspondence. This is a point-to-line correspondence. I know that this point must exist along that line. I really don't know where. Okay, so it's not a homography. It's a looser, it's a more relaxed, a looser relationship than that. Agreed? All right. So this is what epipolar lines look like. So it is, but I don't know that point. I can't geometrically find that point. I have to do an image matching type of, I have to look at the content. I have to do an image matching type of exercise to find that point. Okay. In a homography, I don't have to do that. Once I know the homography, well, to compute the homography, I need image matching. But once I know the homography, you tell me any point, I'll just multiply h and I'll tell you the corresponding point, because there is a unique point-to-point mapping happening there. In stereo, that doesn't happen because the world in general is not planar. Okay, and the camera in general is not just rotating. Yeah.
Are there like cross ratios maintained or something within these lines?
No, not really. That's a good question, but no, right? Because what is the nature of cross ratios being maintained, right? I say if these were two ratios and then this point shrinks, let's say to here, then this ratio would be somewhat here. That's the notion of a ratio, right? But that happens because if the camera is translating, that happens because this world is planar. The whole map of the world stretches or squeezes proportionally in some sense, right? But in stereo, what will happen is that how much this point moves is actually a function of depth. So it's a function of where these points are along the world, right? So if that point is closer to me, it will move more compared to those 2 points which are further away. Think about points along this line. Think about points along this line, okay? And let me draw a map from the top. So the points along this line from the top look somewhat like this, right? This is a 90-degree angle, okay? So it looks somewhat like this, which means between the two images, since this point is closer to the camera, if the cameras were parallel, this point will move more whereas this point will move less, and this will move less, and this will move more, and this will move even less, right? Even less. So all of them would, when I move my camera, all of them would move disproportionately, so no ratios are maintained. And it is precisely the disproportionate motion that tells me how far they are. So it is precisely that disproportionate motion that tells me what is their depth. Okay? All right? Is that point clear? So it's very important to not confuse it with a homography or with homography-like concepts, like cross ratios. Okay? All right, so here's another example. There are a bunch of points here because they were used for estimation, but this is a case where the camera purely translated along the image plane, and so you see that the epipolar lines are parallel to each other. They are not converging. In fact, they are meeting at infinity, because if the camera okay, let me draw that scenario from the top. So there's an image plane and a camera. Okay, and then the second camera is a pure translation along this direction. So there is an image plane and a camera. These are the two cameras. Okay, that's what happened. Now my claim is that the epipolar lines in this case would be parallel, because where is the image of this point in that camera? How do I find that image? Well, how do you find image of any point? You join that point to the camera center. So I'm going to join this point to the camera center with a straight line. And then I'm going to find the intersection of that line with the imaging plane. Well, since the motion happened parallel to the image plane, therefore this line that I drew is parallel to the image plane, and therefore it will meet the image plane at infinity, right? And so that means the epipole is at infinity. If the epipole is at infinity, all the epipolar lines will be parallel. So that's just a proof that in this case the epipolar lines will be parallel. But you can again see that lines pass through same world points, right? If this point is here, well, this point, they're slightly inaccurate maybe, and that's the inaccuracy of estimation, but they are actually pretty close. It's a bit higher than where it should be, and that's inaccuracy of the estimation method which is used here. Okay, consider these two images, 1, 2. Okay, you understand what's happening? So the camera really moved a little bit forward. It's not a plain zoom of the image really. It's actually the camera moving forward, which will generate different disparities, different motion between the. So where do you think the epipole, or how would the epipolar lines look like in this case, if I were to plot on these images? Yeah, they should be emanating from the center, and this is what the epipolar lines look like. In fact, in this case, if I actually physically saw the camera in the second image, I would, if the first image was here, the second image camera is here, so it's actually in the middle of the image, and that's where the epipolar lines are looking like. What do these lines tell me? Well, any point in the scene will only move along its corresponding line, and how much will it move? That's a function of distance. Okay, here's another example I want to spend some time. Okay, so let's now try to, so we understand what the epipolar lines are. Let's now try to look at what will the epipolar lines do? They will help me search for the corresponding points in a more efficient way. Okay, so that's the fundamental nature of epipolar constraint. Now let's say I have corresponding points. How do I triangulate? How do I compute for depth? What's the mathematics of that? So let me first do a very simple case where the camera motion is restricted. One camera is in the canonical view, the other is a pure translation along the x-axis from that camera. Okay, so this is our first camera. Okay, we understand this figure. There is a point xyz in the world. This is the focal length, similar triangles. So x is equal to minus fx over z. Okay, I put a minus sign if the image is behind the camera center. If I put it in front in the virtual camera, I can drop the negative sign. We have seen this before. Okay, so now what if there are two cameras? And these two cameras are in a specific configuration. The camera O1 is in a canonical configuration, and the camera O2 is a pure translation along the image plane direction, along the x direction in the image plane. It's a pure translation by b. B is the baseline, so really the bracket should have gone larger. No, it is actually okay. From the center here to the center, the distance is b. Okay, so there is a translation of x-axis is going in that direction, x-axis is going in that direction, so there is a translation of minus b between the two cameras. Okay, now what I want to do is x and y are two-dimensional entities. Z is really the depth which was lost in this sense. So what I want to do is I want to derive an expression of z as a function of x1, x2, which are the image points, f and b. I've just ignored everything in the y direction, so I can just get a simple expression for this case. Okay, same geometry will hold in the y direction also. Okay, so how do I do that? What I can do is I can find the coordinate p1 and I can find the coordinate p2 and I can back project and make them rays. Okay, let's see how I do that. My claim is I know the expression for x1. It was here. Okay, let's call that x1. So that's minus fx over z. My claim is that x2 is nothing but minus fx plus b over z. Okay, now what am I doing here? Of course, x2 is in the second camera, x2 is just minus f x over z for that camera. But I want to get an expression of x2 within the same coordinate system of x1. I want to see relative to x1 how much this point has moved. So I want to compute them in the same coordinate system. Okay, so what I'm doing is I'm saying this point is really x in the first coordinate system. It's not x in the second coordinate system. Okay, because where is x? X is a bit to the center here. I mean, to the a bit below this line here. So if I just say x2 is equal to minus fx over z, that's incorrect because it's not the same x. Okay, because this x would really have been here, because that's what x there is. Okay, but that's not the case. The image is not being formed here. The image is being formed here. So I have to write this x in the coordinate system here. Okay, and what is that? Since this is a translation of minus b, if I do x plus b, I will get here. From here, I will get to here because this distance is b. Okay, it's kind of like the same trick. I figure out how much camera has moved and I apply the inverse of that to the point. So how much has the camera moved? The camera has moved by minus b. So I apply plus b to the coordinate. I do x plus b and then just do my normal equation. Okay, it's the same trick that we did in camera models. Is that clear to everyone? Do I need to go over this again? It's just defined to be b. We call it the baseline. That's why we call it b as a symbol. It's the distance between the two camera centers, this center and this center. So that's defined to be b. Now you are saying, why is this b? Okay, let me just put some numbers here for you as an example. Okay, so let's say that x was really minus 10. Okay, this distance is 10, so x was really minus 10. Now in this camera, if I work in the coordinate system of this camera, this is minus 10. Okay, but this distance is maybe, well, how much is this distance? It's really this minus 10 plus this b, because that's how much the camera has moved. If the camera was indeed here, it would have been minus 10. If the camera came down minus 10, it would have been 0. If the camera came down 10 more, it would have been plus 10. So it's really x plus b to get to here in this coordinate system, which is really x plus b here should have been here, and that's exactly where the image would be formed. Agreed? Because that's how much I've moved the camera, and that's the only thing which is generating a translation. All right? In fact, every point in the space moves by the same amount here, which is b. Okay, so this is really minus f x plus b over z. The other way to say this is how we were arguing before. If you apply a transformation to take the camera somewhere, you have to apply the inverse of that transformation to the world point. Since I moved the camera by minus b, I have to add b to the world coordinate. All right. Okay. So now what I can do is, well, this is nothing but equal to minus fx over z minus fb over z, right? I can just write that fraction like this, and minus fx over z is nothing but x1. So I got a relationship between x1 and x2. In fact, because x1 was minus fx over z, so what I get is I can now compute for z. I can say z is equal to, I take x1 minus x2 to that side, then I invert the whole thing. So z comes equal to fb over x1 minus x2. That's it, because that's what I was after. I was after finding z as a function of image coordinates, which are these x1 minus x2. Yeah. Yeah. Oh, this minus sign? The minus f? Yeah. That's just, we can write the camera model with the minus sign and without the minus sign. If I assume that the image plane is behind the camera, then I write it with the minus sign because the image comes out inverted. Remember when we talked about cameras first? In fact, the very first relationship we derived was this. Then we said I can assume that the imaging plane is in front of the camera and I can drop the minus sign. In fact, it doesn't matter because there's a minus sign here and a minus sign here, so I'll still get the same relationship if I don't put the minus signs.
What I'm trying to say is the x coordinate of the image is above the origin. So that value is positive.
Which value?
In the first one, if you where the first image.
No, say that. Which one? Which is the first one? This relationship?
When you open x2 up, you can say yes, the first relationship, x1 equal to minus x2.
Okay, which sign do you have an objection to? Well, that's because the image is inverted, right?
So it is inverted, but the coordinate is above the origin.
Okay, so this was a negative number. And so there is a negative here, and that negative will cancel with this. That's why it's above the origin. Right? I mean, this relationship holds for whole space, for the negative side of the space and the positive side of the space. Right? I'm doing it in general. I'm not doing it just for this figure. It's in general, this is true. Okay. So this is a very important relationship, because in this relationship I have captured the essence of the problem. For this simple case where there was only a translation, the distance z in the world depends on the focal length. I've assumed same focal length for both cameras, and it depends on the baseline, the distance between the cameras, and the difference in the image coordinate. Okay. Let's look at that. We call this x1 minus x2, we call this disparity. And so z is really fb over disparity, which means z is really inversely proportional to disparity. Disparity is really how different in location the point is in two images. Okay, so z is inversely proportional to disparity, which makes sense because if the point was very far away, the disparity would be low. If the point is close, the disparity would be high. Okay, if you put your finger here and close your eye from here and here, well, this finger relative to the objects far away moves a lot. But if it was far away, then it moves less. Okay, that's what disparity is. Yeah. No. I mean, because I moved only in x, so every y remains the same, and so I don't really need the y coordinate. But if I moved in x and I moved in y also, then there would be a relationship that would involve both of them. We'll see that in just a moment. Okay?
So if you just move it y, it will still be the same.
Let me come to that in just a moment. The case where we move just in y, or we move in both x, y, can always be reduced to this case that I described. So it's actually not a trivial case. Okay, so this is the basic idea of stereo algorithms. You have two images. Okay, and these two images are taken, so it's still that simple scenario that these two images are taken such that the camera has only translated. Okay, so which means that if I'm looking at a point here, it must be somewhere along this line. And then what we do is we try to find where it is along this line by doing matching. Okay, we try to match that scene content to where it matches best, and we have not done matching algorithms yet. We will do that, but we try to find where it matches best, and then we say, well, that much is disparity. The offset from that point, from the location of that point, is disparity, and that's inversely proportional to distance. Now it might happen that, well, this is a translation only case, but it might happen that in reality your image is not a translation only case. Like the first example I showed you of the building, the epipolar lines were converging. But what we do is we do some transformation, some 2D transformation, actually a homography, to make them not converging. We can, for example, find the epipole, do a transformation that sends the epipole to infinity. That's a homography. And that means you can always come to this case. You can always align along the scan lines. So this case is not trivial. Any other case can actually be transformed to this. I have more to say about that in just a moment. Okay, so these are results. Here are two images. Notice that there is disparity between the images. If I took this picture, let's say picture 1, and I just translated it with a 2D transformation, which is a homography, I just translated it and gave it to you, you should know the difference, because in that case no disparity would have changed, right? No disparity would have been created. But for example, consider the lamp here. Okay, it moves a little bit over that whatever that is, soda can or something. Okay, similarly the lamp moves a bit over this head, and this head moves relative to the tripod at the back. Okay, so which tells you that this is not just a simple 2D Photoshop of the first image. It's actually that the camera was translating. And if we do this, this is the scene. This is the depth ground truth. Ground truth meaning the perfect measurement of depth. Whiter is more closer to the camera, darker is more further away from the camera. If you do a stereo algorithm based on this windowing strategy that I described, try to find the best match of each window, you get something like this. There are some places in the image where you don't find a match, that's shown in blue, but otherwise, by and large, you get correct depth values compared to this ground truth. Okay. This is a much more sophisticated method. My slide is old, so I said state-of-the-art method. It might not be state-of-the-art today. It was some years ago. But this is a much better matching method that puts a lot more constraints than just simple window matching. It put constraints of the nature that if this point matches here and this point matches here, the middle one should match. There's some regularity between the points. Okay, and then you get very, very good results on this easy data set. Okay, so one notion that I want to add to this simple formulation, which I've already said, but I want to formalize that a bit, is that what if the cameras is not at a pure translation? The imaging plane actually translated in 3D, not just in one dimension, in three dimensions, and it also rotated arbitrarily. So camera 2 is an arbitrary rotation and translation on camera 1. Okay, I can always fix the canonical coordinate system on camera 1 if I want to, but then camera 2 is some R and T from that. Okay, now if that's the case, the epipolar lines will not be parallel, they will not be aligned to scan lines. Like the case I showed you, they would not be like that. They would be converging, they might be in the middle of the image, there could be many different configurations. But the claim is that I can always do some 2D homography on each of the image planes, yani some 2D homography on the images to make them like the translation only case, which is illustrated here, which means make the epipolar lines parallel to each other. Okay, so that scan lines align, and pixel motion after this 2D transformation is a pure horizontal motion. Okay, now can anyone give me an argument of just just a kind of a hand waving proof of that should always be possible.
So you're just taking an image of an image.
Yeah or no, not really. I'm given two images. That's what I start off with. I'm saying there are two images and the epipolar lines are not aligned, like that building image that I showed you. The epipolar lines are not aligned. Okay, I'm saying I should always be able to create from those two images through homographies H1 and H2, H1 applied to image 1, H2 applied to image 2, some homographies that I have to figure out. I can always find, I can always convert this case into a case where the epipolar lines are aligned.
Is this the case of rectification? Affine rectification?
Projective rectification, not affine. That's what I'm saying. I should be able to rectify these somehow. Yeah. Kind of. It's. I mean, I think you're right. Let me say that a bit more clearly. Let's say that this is your image one, and the epipolar lines were going like this. Okay, which means the epipole is somewhere here. With a homography, I can move this point anywhere. With some particular homography, if I wanted to, I can move this point here. I can figure out the homography. It's not even a unique homography. Some homography that will move this point here, right? Homographies have the power to do that. So I can figure out what homography will move this point all the way to infinity. I can do that, right? I will do that for the first image. I will do that for the second image. Let's say the lines in the second image were like this. So this is where the epipole was. I will figure out, so this is a homography H1 maybe. I will figure out another homography H2 that moves this point all the way to infinity. Okay, once I do that, these lines between themselves become parallel, but they might not be. After becoming parallel, it might not be that this line, let's say it's passing to coordinate number 10, it's row number 10, the corresponding line might not be at row number 10, it might be at 20. Okay, because I have not enforced that in any way. But even that is just a scaling along this dimension, which is also can be included in the homography. So I can do that afterwards. I can do that correction. So it means that it should always be possible through homographies, through 2D transformation maps, to make the epipolar lines align along the row direction, such that row number 1 here will correspond to row number 1 here, and row number 2 will correspond to row number 2. And that should always be possible through a homography. Okay, so it's kind of like an outline of a proof that I've given you. So if that's the case, the simple case that I showed you in the beginning is actually not so simple, it's quite powerful. And so I can come back to your question of what will I do with the y coordinate? Well, I really don't need it, because I can always say that the motion is along the horizontal direction after rectification has been applied, after this particular rectification has been applied to the both of the images. Okay? All right. So so there's a paper here that I'm referring to, which says how to compute the rectifying homographies for stereo. I'll skip this, and this is a illustration of this fact. We have two images. We have two images of a 3D scene. The epipole of this image is somewhere here. The epipole of this image is somewhere here. I can apply rectifying homographies to them, and these are the two rectified images in which scan lines are perfectly aligned. Okay, and now it's a translation only case. I can search for that translation which matches the feature point. So if I want to find where this point matches, I will look along the same line on the second image and just search along that for a similar feature, and I'll say this is where it is. Okay.
It seems like the floor meets the walls. It was initially a straight line, but now it seems curved.
Which one?
Both images.
What? Sorry.
So the line, the intersection of the wall and the floor.
Oh yeah, this line is a curve,
Yes.
but it was a curve here also.
There is a homography which preserves straight lines.
But that's not a straight line to begin with, so how will it be preserved?
It looks clear, at least in the second image it looks perfectly straight.
No, I mean, this is a straight line. There is a line passing very close to it, and that's a straight line. And this is nowhere, it's nowhere ending here, right? It should have been here if it was a straight
I'm
line.
saying it's like a flow.
No, it's not. It's a round table. you, I mean, put your, when I give you the slides, put a scale on it and see how straight it is. It's not. It's not straight at all. It's a curved table. And there's a wall behind it. Okay. I mean, you can see that clearly from here. This is a straight line, right? So if this was a straight line, it should the table should have been somewhere here, but it's here. The table goes like this, whereas this is the straight line. You thought what?
It was a carpet or something.
No, no, no. It's like a table which is curved and the objects are on that table. Okay, so here's a summary of a full stereo algorithm. What we do is, using some sort of matching algorithm, we first find a few corresponding points. From those corresponding points, we try to estimate the epipolar geometry, and we'll see that the epipolar geometry is actually encapsulated in a matrix which is called the fundamental matrix or the essential matrix. I'll come to that. Okay, but that's just a way to find which lines corresponding to which lines. Then I do apply rectification. The rectification aligns those lines so that my matching can be along scan lines. Then I do, so first I found a few correspondences, but once I've aligned the lines, I can find a lot of correspondences. And every correspondence I find now can be converted through triangulation through camera parameters into a depth value. Okay, really disparity is proportional to depth. So I just find disparity for every point then. Disparity is inversely proportional to that. Okay, so I've said this geometry notion now, and I use this term fundamental matrix or essential matrix. So I'm not going to mathematically do that. I've talked about epipolar geometry in a qualitative way. I'm going to talk about it in a mathematical way. Okay, so is the plan clear? Why do we need to do that? So that we can actually run a full stereo algorithm. Okay. All right. So this is the I have to define some notation now. So let's do that. There's a point P in the world, which I want to compute in the end in the stereo algorithm, but let's just assume there is a point here. And this is seen in the reference frame of two cameras. There's a camera here O left and there's a camera O right. Okay. So the camera projection centers are O left and O right, and they have imaging planes pi left and pi right. Those are the two imaging planes. Now the 3D point, it's actually the same point, but since we have two different coordinate systems, it will have different coordinates in those coordinate systems. So we say the 3D point P is referred in the left image plane, in the left camera as PL, in the coordinate system of the left camera, which is XL, YL, ZL. It's a 3D point still. And in the second camera, it's seen as PR, which is XR, YR, PR. Okay? It's actually the same point, but its coordinate will be different because you are seeing them in two different coordinate systems of the two cameras. Okay? Now the projection of P onto the left and right images, which is like here in the left image and here in the right image, we call that PL, small pl, which is XL, YL, ZL, and small PR, which is XR, YR, ZR in its 3D coordinates. Okay, and ZL will be in the coordinate system, it will be equal to FL, the focal length of this camera, and ZR will be equal to FR in the right camera, because the imaging plane is really at depth FL and FR. So all points on the imaging plane have that depth. Okay, and there is an epipole EL and an epipole ER. This epipole is EL, which is image of the right camera in the left camera, and this epipole is ER, which is image of the left camera in the right camera. Okay, so far I've defined two different coordinate systems. One is the canonical system for the left camera and one is the canonical system for the right camera. Okay, now note that PL and PR actually refer to the same world point, but as vectors they are different because they are in two different coordinate systems. Agreed? So is the notation absolutely clear? Yeah. Cap ZL and ZR? No, cap ZL and ZR are this point. So I mean that has nothing to do with focal length. But the small ZL and ZR are really the focal length. Yes, agreed. Because this distance is the focal length, right? FL, and this distance is FR, and that's true for all points on this plane actually, because it's in that canonical coordinate system. Agreed. All right. So yeah, go ahead. No, I've not taken that assumption. So FL and FR can be different. There's no restriction on that in the derivation. So the camera can rotate and translate, and the intrinsic parameters of the camera can be different. I've not put any restriction on that. Uh, yeah, sure. How we find correspondence? I'm assuming you can find correspondences because we haven't discussed any methods to find correspondences. It does happen that if the baseline is longer, we call that wide baseline stereo, finding correspondences becomes more difficult, even though triangulation becomes more accurate. So that's a fundamental paradox in stereo. Okay. All right. So now I have PL in the canonical frame of the left camera, and I have PR in the canonical frame of the right camera. Okay. I want to relate them, and my claim is that they are related by a 3D rigid transform. There is a rotation and a translation between the two cameras. So I just apply that translation to PL and then apply rotation, and I'll get PR. Okay, this is whatever is the appropriate translation and the appropriate rotation. This translation is really the baseline. It's the distance OR to OL, and R is the rotation between the two cameras. Okay, so assume that one of the cameras, let's say PL, was in the canonical view. Okay, I mean the left camera was in the canonical view. Then I can find the coordinate PR, which was in the canonical view of the right camera, but I can find it in the left camera through this transformation. It's just a rigid body transform which will do the appropriate rotation and the translation. Okay, so PL minus T moves this point by OR minus OL, and then R rotates it to get into the correct frame of one camera. So this relation is important because this relation really allows you to combine those two coordinate systems into a single one, to transform points in the second coordinate system into the first one. Okay. Also note that small PR, which is the image point, is FR over ZR PR. Well, that's what a camera does, right? And small PL is FL over ZL cap PL. Okay, these are just the corresponding image points. All right. Okay, so now there's one really fundamental step that we need to do, and I'll take a few minutes to kind of complete this derivation. So consider the claim I'm making is consider vectors PL, T, and PL minus T. Okay, so here's your center, the camera center O left and O right, and this is a point which is PL in one camera, in this camera, and in the second camera we know how to transform it into the second camera. Okay, so I'm claiming that this vector PL, I'm looking at it from the left coordinate system. So this vector PL, the vector PL minus T, so where is T? T is this vector OR minus OL. Okay, so PL T, and then this PL minus T, which would be somewhere here, which is really what this vector is going to be. Okay, so PLT and PL minus T, they are 3 points, right? So 3 points make a plane. So they are all coplanar in that plane, which is really the plane spanned by these two vectors, I could say. PL minus T, because it's PL and T, so PL minus T will also lie in the same plane. Okay, because it's a linear combination of vector PL and T. Okay, so I'm saying that these vectors are coplanar. If they are coplanar, everyone agrees that they are coplanar? Okay, if they are coplanar, I can write this relationship, What is this relationship? I took the first two of them, T and PL, and I took their cross product. So their cross product must be orthogonal to this plane. It must be the normal of that plane. And then I take the dot product of that cross product, which is the normal really. So this thing is just the normal, plane normal. And then I take the dot product of that, which is this transpose times this. I take the dot product of that with the third vector. So that must be 0 because it's a dot product of two orthogonal vectors. So therefore, I can write this fundamental relationship between these three vectors. PL minus T transpose T cross PL is 0. Agreed? All right. So now, since I know from my previous slide that PR is R PL minus T, so I can take this R to the other side. How do I do that? I multiply by the inverse here. I multiply by the inverse here. The inverse of a rotation matrix is its transpose. So that means instead of PL minus T, I can write R transpose PR here. So R transpose PR whole transpose times T cross PL is 0. Agreed? All right. So this is a relationship that I get. And then I can open this transpose. I know that A, B whole transpose is B transpose A transpose. So which means okay, I'm going to do that later. Now, one thing, okay, I think, yeah, my slide animation was a little bit off. Okay, so this cross product, now I'm going to do one more mathematical trick. Nothing new, just a mathematical manipulation. This cross product I'm going to write as a matrix multiplication. Now I can always do that, right? Because how do I compute a cross product? Let me really do that here. How do I compute a cross product between, let's say, I have two vectors. One of them is Tx, Ty, Tz, and the other one is anything else, A, B, C. Okay, so how do I compute the cross product between them? Well, that's really going to be, the first term is going to be Tyc, okay, Tyc minus Tzb, right? The second is going to be minus Txc minus, well, plus ATZ, right? And the third one is going to be TXB minus TYA. Is that correct? Okay. Now, my claim, so this is what the cross product by definition is. My claim is that I can write it as some matrix times ABC. And that will also be a definition of cross product. So let's just figure out what that matrix is. So the first term is with C and B. So instead of A, I will write 0. What multiplies by A, I will write 0. And then with B, I have minus TZ. And with C, I have TY. Right? So this will multiply with this to give me the first term. And in the second term, with A, I have TZ. With B, I have nothing, so that's a 0, and with C, I have minus Tx, right? And then for the third term, with A, I have minus Ty, with B, I have Tx, and with C, I have 0. So instead of writing cross product like this of a vector T with some other vector, I can write this matrix and I multiply it with any other vector. It will actually be the cross product of this T matrix with that. So the cross product can be written as a matrix multiplication. That's the only claim that I'm making, right? And yes, you see that from here. Okay, so this cross product T cross PL, I can write it as some SPL where S is this matrix. Notice that this that I made here is the same as this. So this is just a way to write cross product. Okay. So I will substitute that here. So what I get is really R transpose PRT SPL equal to 0. That's my constraint equation now. One observation here, what's the rank of S? Can anyone guess? Is it Well, the maximum rank that a 3 by 3 matrix can have is 3. Now, is it 3 or is it less than 3? So, it's 2. Why?
Because parallel lines will have to 0. Cross product of two parallel lines is 0. So a line that's parallel to tx, ty, tz will cross product with that will get to 0. So it's going to lose rank.
That's an interesting argument. I didn't think like that. Yes, yes. Okay, so here's the hint, right? What if I multiply the first column by minus tx over ty over tz, and I multiply the second column by minus ty over tz, and then I add them up? I actually get the third column, right? Because what will happen? 0 plus, I will get minus tz over tz minus ty, so I get ty, but the minus cancels and the tz to tz cancel, right? When I add the second row, I get tz over tz cancel, so I get minus tx, which is here, and the other one is 0. And when I do the third row, I get here minus ty tx over tz, but minus and minus plus, so I get tx ty over tz, and here I get minus tx ty over tz, they add up to 0. So the third column is a linear combination of the first two columns. So the rank is really 2 for this S. Okay, all right, I'm almost done. So I have R transpose P, R transpose S, PL is equal to 0. How do, just retrace your step. How do you get this equation? You really got it by the fact that those three vectors were coplanar. And then you wrote one of the vectors in terms of the other vector, that's all. Okay, so it kind of encapsulates the fundamental geometry of stereo. Okay, and then I'm going to open the transpose. So I can write this as PR transpose EPL, where E is nothing but RS. Because R will come to this side, R transpose will be R, so R times S, I call that a matrix E. Okay, and since S was a rank 2 matrix, I'm multiplying it with a rank 3 matrix, which is R. R is necessarily rank 3 because it's an orthonormal matrix. A rank 3 multiplied by a rank 2 is also a rank 2. So E is a rank 2 matrix. And we call it the essential matrix. And this essential matrix is relating the coordinates of my world point seen in this camera frame and this camera frame. It's relating them in some way. Okay? And one last trick that I will do is I'll just multiply by FR over ZR and FL over ZL. Because the other side is 0, I can multiply by anything and the equation holds. And FR over ZR and FL over ZL are scalar numbers. Okay, so if I multiply by that, I can write the same equation in image coordinates, in the coordinates of image points. So the left image point and the right image point are related by this rank deficient matrix E. So this is the epipolar constraint. The essential matrix E provides a link between the camera extrinsic parameters and the epipolar constraint. Okay, we are out of time, so I have some things to say about this matrix E, but we will start from that next time, inshallah. Okay, any questions? All right, great. We'll take it up from here next time, inshallah.